Good day, class. Today we will discuss about our module 3. The topics will be the derivative, slope, and rate of change. Now, we have talked about the functions and limits in your module 1, and in your module 2, we've discussed about the continuity. Today, we will apply the concepts of limits to determine the derivative of a function. Now, what is a derivative of a function? By definition, the derivative of y with respect to x is the limit of the ratio delta y over delta x when delta x approaches 0. So, the derivative is designated by this symbol. So there are several notations to sim uh, there are several notations used to symbolize the derivative. So the most common is dy over dx, which means the derivative of y with respect to x. Or we can use other variables also. This just means the derivative of the dependent variable with respect to the independent variable. So other notations are y prime, f of x prime, this of xy, and the derivative of f of x with respect to x. So how did we arrive at this definition? So let's say that, let's go here, and we have a function, uh, okay, wait. Y is equal to f of x. Now, suppose that we increase the value of our independent variable x by a small increment, delta x. So if we change x to delta x, our y must also change. And what is that change? We can say that our function y also changed by an increment of delta y. Now, to solve for the derivative here, we isolate first the delta y. So we have delta y equals f of x plus delta y minus our y is equal to our delta x. And we divide this function by our delta x. So plus f of x plus delta y minus f of x over delta x. Now, to solve for the derivative of the function, we simply solve for for the limit. So we solve for the limit of this function as our delta x approaches 0. So same here. We get the limit. We get the limit as our delta x approaches 0. So this will be the fundamental concept of derivative. Now we have steps to follow in solving for the derivative of x. These are general steps and very easy to follow. It's straightforward. So you can just, I will show you how to apply these step procedures into our sample problem. So basahin nyo na lang ito, class, ha? Now, for again, I have provided an example for you to familiarize with the steps. So I've indicated what steps have I used in my solution. So basahin nyo na lang ito. Next, our derivative Now that we know how to solve for the derivative of a function, we now proceed to its application. So why is the derivative of a function very important? Because of its application in engineering. So one of the application of derivative is to solve is it can be used to solve for the slope of a function at any point. So by definition, the derivative of a function is identical with the slope of the graph of the function. So you can just read this our module. And again, I have provided another example for you to be familiarized with this definition. So basahin nyo na lang to. So ito yung solution. Let's zoom it out so that everyone can, so that you can see it. So yan, okay na. So pause nyo lang and basahin nyo na lang. Now let's proceed to another application of the derivative, which is the rate of change. So by definition, the rate of change is identical to the derivative of a function. And why is it very useful, the derivative? Suppose you can appreciate it class when you solve problems. But let me give you an example for you to visualize or appreciate the application of derivative for the rate of change. Suppose you are doing a survey and you want to determine the speed of a certain car. So what you do is you put two posts, post 1 and post 2 at a known distance. So what is the formula for the speed? It is the distance, the total distance traveled over the total time. That will be your average speed. Suppose that your car travels at a uniform speed, at a constant speed, so that the speed of the car at any point is the same between this post. Now to get its average speed, we simply divide the distance, which is known to the calculated or the recorded time. So that will be the distance. But suppose that the car is traveling with varying speed. Now we can still use the formula, total distance over total time elapsed. But you will get the average speed for this whole distance. Now you want to solve for its let's say point speed or its speed at a certain point between the posts. So how can you do it? Or what can you do about it? So let's say that you want to solve its speed at a certain point, say here. What you will do is you decrease the distance between the two posts, so that when you decrease the distance at the between the points, its travel time will also decrease. So it doesn't have enough time to vary. So the speed doesn't have enough time to vary, or in other words, we can say that as the distances between the 2 points approaches zero, the change also in time that the car travels also approaches zero. So you can get the distance between, you can get its speed at a certain point. So that's the concept class. And I will solve a sample problem to demonstrate its application. Now, also I have provided an example problem for the rate of change, and I mean an example for the rate of change. You just read it, class. Now, let's move on to our sample problem so that I can discuss to you how the methods is used. And in our next module, we will derive formulas for the derivatives of algebraic function. This method is this long solution is helpful for you to be familiarized with the principle. But during the course of our through our semester, we will use our formulas to determine the derivative of functions. This is important class, the long solution, because I want you to be familiarized with the concept and not just use formulas, because formulas are useless if you do not know the concepts behind it. Memorization in engineering is not practical. In high school class, maybe you are taught to memorize formulas or uh, other stuff. But here, in engineering, I want you to be familiarized with principles so that you can derive formulas even if you forget it. Okay. Now let's solve our sample problem. Okay, class one. Okay. Okay na to. Yeah. So our sample problem would be, find the slope of the curve y squared equals 3x plus 1 at 1, 2. And we are also asked to graph the given curve and show the tangent line at the point of intersection. Okay. So this is the application of a derivative to find the slope of a function. Now, what? Let's first write our given. Okay. Zoom in lang natin, class. Mhm. Okay, what is our given function? Y squared equals 3x plus 1. And what is our given point? Given point is 1 and 2. Now, what is our required? The slope or the first derivative of the function. Now, how do we solve this class? First, I want, in general, when you are solving problems, there is a given function, there is a given point. First, verify if the given point is actually on the curve. So let's try. We can do it. Where is my calculator? We can do it, class, using our calculator first. So what is our function? X, I mean, wait, 3x plus 1. So when x equals 1, our value is 4. So what about y squared? 2. So 2 squared is 4. So definitely this point is on the curve. Now let's try to solve the class. So what is our solution? So first step is we write the given function, and then we assign an increment for for our x, say delta x, and of course we will have a corresponding increment in y, say delta y. So we have y plus delta y squared equals 3x plus 1. Now this is a perfect square trinomial. Let's expand this class. Y squared plus 2y delta y plus delta y squared equals 3x plus 1. Okay, now our next step will be to isolate delta y. So, but can you not, do you notice, class, that we have an expression delta y squared? So how do we attack this problem when we encounter such expressions? Remember, class, that our delta x is very small. It approaches 0. If our delta x is very small, if the change in x is very small, then delta y, or the change in y, must also be very small. So what happens when you square a very small number? What happens first? It becomes 0, or it practically becomes 0. So our expression here is practically 0. So try nyo lang, class. 0.0001 squared. So what will you get? Practically 0. So our expression would become 2y, I'm sorry, 2y delta y equals, let's transpose y squared to the right side. We have 3x plus 1 minus, I'm sorry, we have, this should be x plus delta x plus 1. Sorry. At 0. Okay, let's go back to the boundaries. Let's isolate first this expression. So we have, let's expand this expression. 3x plus, sorry, 3 delta x plus 1 minus y squared. And then we divide this one by 2y. So we have delta y would be, so let's first rearrange this expression terms. 3x plus 1 plus 3 delta x. So our y squared is equal to 3x plus 1. So that these two expression here, sorry, will be cancelled out. And then we divide it by our 2 delta y. But what is the value of y? Of course, we have square root of 3x plus 1. Here, let me first clarify, class, that the square root of when we get the square root of our function, the right side must be plus or minus square root of 3x plus 1. But here in calculus, we are omitting the negative root. We are always using the positive root. So that's just a clarification. So okay, we have delta y equals 3 delta x over 2 square root of 3x plus 1. Okay, we divide both sides by delta x, delta y over delta x equals 3 over square root of 3x plus 1. Yeah. Now, the derivative of the function is equal to the limit of delta y over delta x as our delta x approaches 0. So we have the limit of 3 over 2 square root of 3x plus 1 as delta x approaches 0. Now, from this expression, wala na tayong delta x. So as is siya. So y prime is equal to 3 over 2 square root of 3x plus 1. Okay. Now that we solve for its derivative, we can solve for the slope at the given point. So x equals another given point natin plus 1. X equals 1. Or y prime is equal to 3 over 2 square root of 3, 1 plus 1. Which is equal to 3 over 2 the square root of 4, so this is 2. Okay, so our y prime is now equal to 3/4. Yeah. Okay. Now we are asked to graph the function and also graph the tangent line and its point of intersection. So how do we do it, class? Okay. Remember in your analytic geometry how to graph given the given functions? Balikan nyo na lang. Because, pero i-discuss ko. I will show it how it's done. So our function is y squared equals 3x plus 1. So ano bang nakikita niyo dito? At first glance, anong graph niya? It is a parabola. Yes. So let's first write the standard form of a parabola. So our standard form of a parabola would be wait, y minus k squared equals, oh sorry, um, b equal to 4a x minus h. So let me give you a short review. Our hk is the vertex of the parabola. Our 4a is the latus rectum. Yes, latus rectum. And if it is positive, it opens to the right. If it is negative, it opens to the left. If the square is in the dependent, it is the y, it is symmetrical about the x-axis. If the square is in the x, it is symmetrical about the y-axis. So yeah, yes, okay. So since it is squared at the y variable, so it is symmetrical about the x-axis, we can verify it class by using the symmetry test. Just substitute negative y to y, and if the function does not change, then definitely it is symmetrical about the x-axis. Let's find first its vertex. So from this standard form, we have the vertex will be, let's factor this out, 3 x minus. Okay, now our vertex would be equal to negative 1/3 and 0. So meron na tayong vertex. Alam natin na it opens to the right, and alam natin na symmetrical siya sa y-axis. We can graph. Okay. Let's graph. Let's graph. Sorry. Wala kasi. Kaliwete ako class, kaya kung napapansin nyo, nagsisimula akong mag-trace from the left papunta na rin. Okay. Now suppose our vertex is over here, and this point is wait lang. Let's say negative 1/3. I'm sorry. Negative 1/3 and 0. So our graph would be like this. Oh. Yeah. Our graph would look be, oh, sorry. So that would be our graph. So this is sorry. Y squared equals x plus 1. Okay. Now, how about our tangent line? So our point is 1, 2. So suppose nandito siya 1, 2, 1, 2. This is 1, 2. And our tangent line will be here. Please. Hi. Ba to? Ganyan. So, yan na class. Yung ating graph of the curve and the tangent line. And it is important to note, class, that the slope of the tangent line is always equal to the slope of the curve at the point of intersection. So, okay na class. Let's move on now to our next example problem. So, okay.